Okay, so here we take a look at how to really solve a constant coefficient linear ODE with three steps. So actually, for an arbitrary constant coefficient ODE, we can write it like this. Okay, so on the right side, we have g of t. Okay, so on the right side, it only relates to the dependent variable. In our case, we consider t is the time. Okay, so on the right side only related to the time, but not the unknown function. Okay, so it is just a function of time. Of course, it can be a constant. Okay, but it can only be at most related to the time. It can be arbitrary function of time. It doesn't necessarily to be linear. Okay, it can be t squared sine of t or whatever function of t. Okay, or any combination of them of the function of t. Okay, so on the left side we have linear ODE, so we can only have the nth derivative, n minus 1 derivative, all the way down to the first derivative and the original function of x. And then here x is the unknown function that we'll like to find. Okay, and on for the coefficient, okay, as much as this is constant coefficient, so which means that all the coefficient of these derivative terms are all constant. Okay, so an is a constant, an minus 1 is a constant, all the way down to a0 are all constants. Okay, so in such a way, this is a constant coefficient linear ODE. Okay, so the first step to do, here is to make the right hand side to be 0. Okay, so we just keep the left side of the constant coefficient ODE, and then we let the right side to be 0. Okay, so in such a way we call this one, okay, of course this one is strongly related to the original constant coefficient linear ODE. Okay, but we just make we just remove this part at the first step, Okay, so we try to solve this first, and this one we call it a homogeneous equation, and the solution for this homogeneous equation is the homogeneous solution. Okay, so and later on we would like to find the solution which is related to the g of t, of course related to the left side, but the solution related to g of t, we call it particular solution. So this will be the second step. Is to find the particular solution, and then the third step is to just add them together. Okay, so for the third step, we try to add them together. So we have the complete solution to be the x of t, which is the homogeneous solution plus the particular solution. Okay, so you may ask, why we use c here rather than an h. Okay, so actually for some of the mathematics textbooks we will call it a complementary solution. Complementary solution， 那中文叫做互补解。那这个就是 so these two are actually having the same meaning. So here I just call it the xc of t, which is known as the homogeneous solution or the complementary solution. Okay, but for the particular solution, usually you just call it particular solution. So the complete solution will be the homogeneous solution added with the particular solution to be the complete solution. Okay, so finally we should use an initial value. So this may be a tail. So sometimes we don't need to do it, sometimes we can do it. Okay, so if we have something called the initial value to determine the unknown coefficient, we can actually determine the unknown coefficient, because for the complete solution it consists of course, this part and this part. Okay, for the particular solution, it can only be a unique solution, but for this homogeneous solution, it should have a set of infinite solution. So it, or in other words, it will include some unknown variable that need to be determined. But whether we can determine this unknown coefficient is that we need some initial value or initial values. Okay, depend on how many orders is the ODE. Okay, so if it is a first order ODE, we need one single initial value so that we can we can determine the unknown coefficient for the complete solution to make it a unique solution. Or if it is a second order ODE, then we need two initial values. Okay, so this is quite abstract at this moment. So let's see how we can really do it. Okay, so here is the first step is to solve the homogeneous solution or solve the homogeneous equation for the homogeneous solution. Okay, so here we just let the right side to be 0. Okay, like this. Okay, so of course, in general, this is an nth order homogeneous equation, and here to really show how to solve it, we just make it like n equals 2. Okay, we have a second order homogeneous equation. Okay, we will transfer this into a second order algebraic equation. So I suppose you should have learned it in junior, I think junior 2 or junior 3. Maybe junior. I don't really remember, but probably junior 2 or junior 3. Okay, so we will turn a second order homogeneous equation into a second order algebraic equation with one unknown. Okay, so if it is an nth order homogeneous equation, we will turn it into an nth order algebraic equation. So in such a way, you know how to solve a second order algebraic equation. You probably know how to solve third order, fourth order. But yeah, maybe in general, for the equation higher than fifth order, higher or equal to fifth order, it may not have a closed form solution. But yeah, but at least you should know how to solve a nth order algebraic equation. Okay. So here, for demonstration, we just show the case of a second order homogeneous equation, and then we will just turn it into a second order algebraic equation. So here, rather than call it A2, A1, A0, we just call it A, B, C here. Okay, so for the coefficient of the second order, third order, and the original function, so we just call AX double prime, and then plus BX prime plus CX equals 0. Okay, so here we have a second order homogeneous equation, and here we try to guess. Okay, we try to guess the solution of this second order homogeneous equation. Okay, so just pretend we are very lucky or very intelligent to guess the correct solution. Okay, so we just assume this solution should have a form of exponential to st. S will be an unknown variable, and then t is this dependent variable. This t is this dependent variable. Okay, so you just assume that we are very lucky, so we assume the correct form. Okay, so maybe you ask, why we know that the form should be like that. Of course it is really the correct solution, and if we need to say that this one, okay, of course you should have learned the calculus 1. Okay, so you know taking the derivative of an exponential function will be itself and then multiply by this s, okay, with a chain rule, okay. So in such a way, we will have, as much as we have the original function and its derivative. So if we assume the form of a solution like this, then after plugging it back to the original homogeneous equation, we will also have this function, and then finally we can cancel it out. So yeah, so it's just like we know the result is correct, and then we try to explain. But of course you may just remember, okay, this is very useful, okay. So assume this is okay, and then we try to plug this solution back to this homogeneous equation. Okay, so for this one, plugging back to here and then taking the second derivative, we will have s squared coming out, and then of course multiply by this exponential to st, and then of course with this a, okay, for the first term. And then for the second term, it is easier. So we have b here, and then the first derivative of this one, of course we have exponential to st, and then for the chain rule we have s, okay, because it is the first derivative, we have an s here, okay. And then for the last one, the most easiest one, because we just put it there and then it's done. So we have c times exponential to st equals 0. Okay, so we have, okay, after plugging in the assumed solution back to the original function, back to the differential equation or the homogeneous equation, we have an equation like this. And then here we can just divide by the whole equation by exponential to st, okay, because exponential to st can never be 0, okay. So we can be safe to really divide this term, okay. So actually it's just like we just cancel all this stuff out, okay. So finally we have as squared plus bs plus c, okay, equals 0, okay. So s is an unknown variable, okay. We have a, b, c are actually this coefficient. So at the very beginning, a, b, c are known variable, okay. So finally it turns out like we have a second order constant coefficient ODE. We turn it into a second order algebraic equation, okay. And then we will call this one and the auxiliary equation, or for some textbook we will call it the characteristic equation. OK， 那这个叫做特征方程，或者这个叫做辅助的。那可能就是 characteristic equation 反而叫的比较多一些，就是反正有很多名字了。那意思就是一开始我们有一个二阶的常微分的一个 homogeneous equation， 那我们把它变成二次的代数方程。那代数方程的话就是初中生都会的Okay, so here let's summarize a bit what we have done. Okay, so originally we have this second order homogeneous equation, and then we try to assume the solution of this homogeneous equation to be like this with an exponential to s of t. Okay, so and then after some calculation, we know that we should have as squared plus bs plus c equals 0. Okay, if s satisfies this equation, then this one should be a solution to this homogeneous equation. Okay, so the logic should be like this. Okay, so for a junior student, okay, should know, okay, for this second order algebraic equation, we should have three cases. Okay, which is a delta equals b squared minus 4ac, okay, b squared minus 4ac. Okay, so b squared minus 4ac can be either larger than 0, equal to 0 or less than 0. Okay, so we have 3 cases. Okay, so we try to talk about it one by one. Okay, so for the first one, b squared minus 4ac is larger than 0 should be the I suppose it should be the most trivial one, okay, most easiest one, even for this one, okay, when you learn it in junior school, okay, this one when delta is larger than 0, this equation will have distinct real roots, okay, 有这个相异的实根啊，相异的实根 distinct real roots S1 and S2. Okay, so which means that if S equals to S1, it should be a solution to this equation. If S is equal to S2, this one is also a solution to this homogeneous equation. Okay, so finally, the complementary solution or the homogeneous solution will be like we have this exponential to S1t, exponential to S2t, but we also have C1 times this exponential to S1t plus C2 times exponential to S2t. Okay, why? Why? Okay, so if you still remember, we talked about the linear condition for the the linear. What is linear? Okay, so here, suppose we have a second order homogeneous equation, and then if we know, let's say this a d2x dt2 plus b dx dt plus c equals 0, we can actually return it as something like f of x of t equals 0, f of x of t. Okay, so we can consider this stuff is a function of x of t. Okay, so in such a way, if we know that x1 and x2, x1 equals exponential to s1 of t is a solution, and also x2 equals exponential to s2 of t is a solution, are also the solution of this capital F, which means that we should have f of x1 of t equals 0, and also we have a f of x2 of t equals 0. So with these two conditions, and then suppose we use this linear property, so in such a way f of let's say c1 x1t plus c2 x2t, okay, using this linear property should be like c1 f of x1 of t plus c2 f of x2 of t. Okay, and here we already know that this one and this one are 0. So this one is 0. This one is also 0. So it's equals 0. And this one, we assume this is just the complementary solution. So which means that this one, if we just substitute this homogeneous solution into the same homogeneous solution, it should be equal to 0, which means that xc of t should also be a solution to this same homogeneous equation. Okay, so that's why here we know that this one is a solution, and then this one is a solution, so that we just multiply them by two different constants, and then add them together. This big thing should also be a solution to this homogeneous equation. Okay, so this is the first case, which is, I suppose, which is the most easiest case to understand or to remember. Okay, for the second case, b squared minus 4ac is equal to 0. Is equal to 0. Okay, so we know that for this case we should have repeated real roots. Okay, 有重根，有重根，实数的重根。Okay, which means that s1, s2 should be equal to each other. Okay, in such a way, if we still follow this case, okay, then the problem will be like xc equals C1 exponential to S1t plus C2 exponential to S2t. Okay, but actually S1 and S2 are equal to each other. So it turns out to be, this one is also S1. Okay, so it turns out to be C1 plus C2 exponential to S1t. Okay, we only have a single solution. Okay, this one, an arbitrary constant plus an arbitrary constant is still a big constant. So this is just nothing but a C. Okay, so this is not okay for the second case. So in such a way, so this is not good. This is not good. So yeah, if you just want to remember what is correct, okay, so what I tell you is that you really need to multiply this one by a t. You need to multiply this one by a t. Okay, so yeah. Okay, so originally you can consider this is something like this is just a c exponential to s1t. Okay, so here this one should be somehow like extend to a first order polynomial， 就是一次的多项式，它变成有一次项跑出来，那你可能就记住它吧。记住它，就是重根的话，就会有一个 t 跑出来。那如果你真的要问为什么的话，那你可以做的事情就是说，we try to assume as if we already know that b square minus 4ac is equal to 0, you can assume that xc of t equals to, let's say, g or let's say h of t times exponential to s1t. Okay, so we assume this is also a solution. Okay, why? Okay, so yeah, one reason is that it really works, and why we assume it is a function multiplied by this thing. Okay, so because this is already a solution, so we may also guess that the second solution also related to this function. Okay, so we try to multiply this thing to the original solution. Okay, so we hope that this is also a solution. Okay, if you just use add, then this is nothing because the original thing also has this one. So we try to use multiply rather than addition. Okay, so in such a way, if you just putting this thing into the original differential equation, then you may be able to find that this is a first order polynomial. So which is something like this. Okay, so yeah, so if you have interest, you can try to do this by yourself. But otherwise, you can just simply remember that if we have repeated real root for the auxiliary equation or the characteristic equation, then this will be this function multiplied by a first order polynomial. Okay, so this is the second case. And then for the third case, okay, which is the most complicated one, but it will be the most useful. Actually, I think the first two will be the quite useless. Okay, for most of the case, what we would like to use it is for the third case, but actually this one is the most complicated one. So even for when you learn it in junior school for this second order algebraic equation, okay, as much as b squared minus 4ac is less than 0, you know the solution is a complex number, okay, which is supposed to be the most bothering things, okay, because at least you need to know what is I equals square root of -1. Okay, so actually, when b squared minus 4ac is less than 0, so we should have a complex conjugate roots. Okay, 这是共卧复根啊，共卧复根。Okay, so let's denote it as alpha plus or minus I beta. Okay, 共卧就是一个是加一个是减嘛，然后 I beta. Okay, and try to keep it in mind that sometimes I will call it J. Okay, because for electrical engineering, I think all the textbook in the electrical engineering use J rather than I, because we already have I used for the current. Okay, for the current. So I always reserve for the current, and we always use J to represent the negative or square root of -1. 就是我们永远都是用 J 的，就是我没有看过电机的课本是用 I 的。Okay, so yeah, so 所以就是记住，有时候我会写 J， 就是因为习惯了，就是对，就是20年都是这样写 J exponential to J 什么的。那这边有些就是写了 I， 就是对。Okay, so actually, if we have a complex conjugate roots, okay, so the solution look like this. Okay, why? Okay, we have exponential. Yeah, we can somehow understand. Okay, because we have an exponential to something. Okay, so we still have exponential to something, but why we have a cosine and sine here? Okay, so to really understand it, we need to understand something called the Euler's formula. Euler's formula. Okay, for the Euler's formula, it is something like exponential to j theta equals cosine of theta plus j times sine of theta. Okay, so it is always true. Okay, for theta can be any real number, or theta any complex number is also okay. 所以它实数这个是正确的，复数也正确的。为什么它是正确的？你可以用一个，如果是我们是工程学生的话，可以用一个比较简单的方式去验证它是正确的。就是对数学系的同学来说，就说你这个不是很严谨，你都没有考虑它是不是收敛。但是如果工程的话，我们就接受。大概的意思就是说，我们知道这个跟这个的Taylor series expansion 或者叫做 Maclaurin series expansion. So we know that exponential to x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial all the way up to infinity. Okay, so we also know that cosine of theta equals 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial all the way up to infinity. Also, we know that sine of theta equals x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial plus all the way up to infinity. Okay, so we know, suppose you have learned the calculus. You should know the Taylor series of this well-known function. Okay, so we just need to substitute x by j of theta for the first one. Okay, so here we will have something like j times theta, and then here we will have a negative sign, and then theta squared. Okay, so it will be this one. Okay, because if we plug in, so here we have a theta square, but with a negative sign. So here is a j square or I square will be -1. Okay, something like this. And then here also j theta all the way to this third power. Okay, I mean the whole term's third power. Okay, we will have a negative j times theta square, theta cube. Okay, which correspond to this term. Okay, so we can simply verify that this is correct. This is correct for the real number of x, or even, or maybe you can just use theta here, theta here, theta here. Okay, a real number of theta, or even complex number of theta, it is also okay. Okay, so in such a way we have this thing. Okay, we have this thing. Just assume that this is correct, and according to this one, we can have a quick variation of it to be like exponential to negative j theta will be cosine of also theta. Okay, because if you just substitute theta to be negative theta, theta to be negative theta, cosine of negative theta is cosine of theta. Okay, cosine is an even function. Okay, so cosine of negative theta equals cosine of theta. Okay, but here cosine of negative theta will be negative j sine of theta. Okay, so this is a variation of this Euler's formula. Okay, so in such a way, we can make use of this to really understand why the complementary solution for the third case to be like this. Okay, so here, suppose we have a S1 equals alpha plus, let's say I beta or J beta, and then S2 equals alpha minus J beta. Okay, these are S1 and S2 are complex conjugate roots. Okay, so which means that x1 equals exponential to S1t, and also x2 equal exponential to S2t are a solution. Okay, so in such a way, using the idea of the first case, we can write it like xc of t should be something like, let's say, c1 exponential to S1t plus C2 exponential to S2t. Okay, so here we try to plug in this one and this one to here and here. So here we have a C1 times exponential to alpha plus J beta t plus C2 exponential times alpha minus J beta t. Okay, something like this. We just plug in the expression of S1 and S2 to here. Okay, so in such a way we have exponential to a sum or exponential to a difference. Okay, so in such a way we have a C1 exponential to alpha t times exponential to J beta t, and then plus C2 exponential to alpha t exponential to negative J beta t. Okay, so yeah, exponential to this one, so we just multiply together, multiply these two things. It will be this one, and then this one exponential to alpha t, exponential to alpha t, exponential to negative J beta t will be this one. Okay, so here we can clearly see that this is the common factor, so we can just put it to the front, and then we have a C1 exponential to J beta t plus C2 exponential to negative J beta t. Okay, so here we have this thing, which is actually this thing. Okay. So here we try to understand why the later part becomes cosine and sine. Okay, so this thing becomes cosine and sine. Okay, so when you just look at the two form of the Euler's formula, okay, so this thing can become cosine and sine, okay. So yeah, we have a little bit idea about that. So here, let's try to expand it like C1 cosine of beta t plus J sine of beta t, and then plus C2 cosine of beta t minus J sine of beta t. Okay, so here we try to correct the term. So finally we have cosine of beta t, okay, which is this thing and also this thing. Okay, so which is C1 plus C2, and then for the second one we have a sine of beta t. sine of beta t. Okay, it should be like C1 minus J times C2, sorry, it should be like J times C1 minus C2, J times C1 minus C2. Okay, so and yeah, you will say, oh, this is a complex number, so how can it be a real number? Okay, so and actually we can just call it C1 cosine. Okay, maybe we just call this thing C prime, something like this. Okay, C prime all the way. Okay, so finally we can just call it C1 cosine of beta t plus C2 sine of beta t. Of course, you may still ask why this thing can become a real number. Okay, the idea is that originally this homogeneous equation is a real function with real coefficient. Okay, so we should expect the solution should also be real function. Okay, so in such a way, we will expect this original C1 prime, C2 prime should satisfy some condition, which is C1 should be the complex conjugate of C2. Okay, complex conjugate 就是 C1 prime 跟 C2 prime 是共卧的。那这样的话，这个就会变成实数，因为它们相减之后，它们就会变成一个纯。如果它们是共卧的话，相减之后就只剩下序数的部分，再乘一个 j 就会变成纯实数。那相加的话，共卧的话，序数的部分就会抵消掉，所以这个又会变成实数，这个又会变成实数，所以就会有这个条件的出现。那我们就会有C1 C2 是实数啊 ，C1 C2 是实数啊，是实数。所以 so in such a way, if the complex conjugate with alpha plus or minus I beta or J beta, then we will have this real part putting here exponential to alpha t, and then this is the imaginary part. Okay, imaginary part. So we just put it in the beta here. T is the dependent variable. And then we have we call it the linear combination of cosine of beta t and sine of beta t. 那我们在线性代数里面就会把这个东西叫做线性组合，就是 cosine of beta t 跟 sine of beta t 的线性组合。意思就是说，我们把这个跟这个乘以一个常数加起来，这个就叫做线性组合。原来那两个函数的线性组合，然后再乘这个，就是第三个 case。那这个最有用的，因为它有 cosine 跟 sine 出现。Okay, so here we say C1 and C2 are arbitrary constant, which should be determined by the initial value later on. Okay, all these three cases, C1, C2 can be arbitrary values. Okay, we cannot determine what they are yet. Okay, as much as we know the initial value. Sometimes we will know it, sometimes we don't know. If we know that, then we may be able to determine the unit value for C1 and C2. But if we don't know the initial values, then we may not be able to know C1 and C2. Just let it an arbitrary constant or arbitrary variables there. Okay, so here we have some simple samples, so you can familiar with what is going on. So it is not that complicated. Originally it's like very complicated, but actually you can just remember. Okay, for the first case, the solution like this. The second case, the solution like this. The third case, the solution like this. And then you can just write out the solution very quickly. So for the third case, 2x double prime minus 5x prime minus 3x equals 0. Okay, so to write out this characteristic equation or the auxiliary equation, we just change the second derivative to a second order, to the s square. The first derivative become an s, and then the original function become a 1, okay? So change it to s squared, change it to s, change it to 1, okay? So here we have a 2s squared plus minus 5s minus 3 equals 0, okay? So to solve it, we have a s1 equals negative 1/2, and then s2 equals to 3. Okay, so these are distinct real roots, okay, which means that the complementary solution to this homogeneous equation, or if it is the original differential equation, the solution will be c1 exponential to this is s1. S1 is negative 1/2 times t. So this is negative t over 2 plus c2 times exponential to 3. 3 is s2 times t. Okay, so this is for the first example. For the second one, x double prime minus 10x prime plus 25x equals 0. Okay, so this one is s squared minus 10s plus 25. Okay, so s squared minus 10s plus 25 equals 0. Okay, so here we can clearly see that this is s minus 5 whole square. So which means that the solution to this second order equation is s1 equals s2 equals 5. So which means that the solution to this second order ODE is c1 plus c2t. This is repeated real roots, c1 plus c2t times exponential to this s. S is 5 exponential to 5t. And then for the third case, x double prime plus 4x prime plus 7x equals 0. So here we have a s squared plus 4s plus 7 equals 0. S squared plus 4s plus 7 equals 0. So s1 is a negative 2 plus or minus square root of 3i or square root of 3j. Okay, so in such a way, the real part is negative 2, the imaginary part is square root of 3. So the solution to this second order ODE is exponential to negative 2. The negative 2 is this real part, and then for the square root of 3 is the imaginary part here. Okay, so exponential to negative 2t times c1 cosine of square root of 3t plus c2 times sine of square root of 3t. So actually you just need to slightly remember why these three, what is the solution for these three cases. Then you will be able to write out the solution to the second order homogeneous equation very quickly, as much as you know how to solve the algebraic second order algebraic equation. Okay.